Hello, I'm Kutay. Today we're gonna talk a little bit about modeling smart meter data. Why do we do it, and how we do it? How do we do it? So a little bit of a disclaimer. It's not gonna be a research outreach or anything like that. I want to give you some fundamentals and what I get from this topic, so that maybe we can meet in the common point and maybe discuss some next research opportunities, and without going into details, and we can look it from the bigger perspective. So here's the planning. I have a natural break in the middle, which is called lunch. And before the lunch, we're gonna cover some high-level topics. We're gonna try to understand the role of smart meters in modern energy systems. Then again, we're gonna try to still understand what is generative data modeling, and we're gonna combine these two with in the smart meter data modeling realms, and we're gonna talk about the associated challenges. And after the first session, we're gonna get our hands dirty, and we're gonna try to apply these in variational autoencoders. What are variational autoencoders? First, we have to discuss about that. For that, we're gonna dive in a little bit of a math, but promise I'm not gonna drown you with lots of math, hopefully. And then I'm gonna open some notebooks, which is in Google Colab, and you can follow it, and later you can play with it if you will. Yes. So, first of all, who am I? I'm much younger. I'm Kutay from Istanbul, a little city in Turkey. Lots of people. Kadıköy is a little town in Asian side. If you go there, please taste the breakfast. It's amazing. And how did I come here? First, I got my bachelor degrees in Istanbul Technical University, and I was a communications engineer, and I had nothing to do with any of these. I was doing some modulation schemes for 6G communication systems. Then I did another bachelor's degree on control and automation engineering, some wireless localization learning. Then master's degree with control and automation engineering, again, some interpretable AI with autoencoders and fuzzy logic. Now I'm a PhD in electrical sustainable energy department of TU Delft, and my main topic is synthetic smart meter data generation. And as you can see, things are getting more data sciencey throughout the years. So that's where I am right now. So that's maybe give you some heads up for the rest of the presentation. So what are the contents for the first part? First, some introduction. Actually, I already gave the introduction. Then I'm gonna give you some clues. What are the smart meters and why they are used, why they are important. Some data modeling or generative modeling, if you will. And then I'm gonna talk about the associated challenges. Lastly, I'm gonna conclude and then we're gonna go to our lunch, at least the physical. So smart meters. We probably all heard about those. Maybe you all have those in your house. What are they? Those are basically measurement devices that counts how much energy that you consume or produce. It's also a good advantage of those. And unlike the conventional meters, they are two-way. Normally, normal meters are only one way. They can only send information to the system operator or utilities. But in the smart meter case, they are communicate in two ways. And that's pretty much it. Actually, they are super simple to understand, but super important. Why? So first of all, they are really high in resolution. Normally, if you remember, or if it's still like that, I don't know. Normally, a guy from the utility company or supplier side comes to your house, and read the metering, like your readings, and then go to the office or, directly bill you there, and you have to pay, right? And it's maybe once in a month, probably once in a month, but in Europe, I think once in a year, maybe. But in the smart meter case, this is not the case. They send data in hourly resolution, and they read the consumption actually in seconds, maybe in 1 second, 5 seconds, in every 1 second, 5 seconds. It's very high in resolution. But generally, the utility companies have the hourly resolution data, which is a great thing because it gives a lot of observability in terms of time. And also, they are really high in resolution in space. So as you might know, in the power systems, we have some, if I'm wrong, please correct me. We have substations, radios, and everything, but not all of these are super observed. Of course, we have some SCADA systems, some PMUs, but they are expensive things. It's not easy to install all of those in the network that easily. So instead, why don't we use the smart meter data, right? Because we already know the location of each customer, which feeder or substation they are connected to. So we can just aggregate the smart meter data and boom, we have the readings for the substations, which is a great thing. I mean, not super high resolution, but still better than nothing, right? And yeah, this is also another thing. For example, in the Netherlands, I mean, of course, there was some issues in the that was compulsory at first to have a smart meter. Then they took it back, etc. But still, everyone has a smart meter. Most of the people, like 80%, 90%, and they are already installed. So there's a big potential to observe the network, which is a great thing. So zero investment. So what are the potential applications? Grid management is one of them. So we can enhance the load balancing, stability of the power grid. Of course, by facilitating the real-time station, because it's like 1 hour is not real-time, but still better than 1 month. And some fault detections. These are really important for operators. We can also design some tariffs from the supplier side, so we can induce more sustainability, less emission. We can shift the peaks. We can have more flexibility, etc. And also demand side management is pretty much the same thing, but from different sides. One of them is from the supplier side, the other one is from the much more like a customer side. We can manage the demand side by using these data, or like the measurements. And there are lots of other applications too. Some renewable energy integration, because we also can detect the production of the houses with PV panels, and also electrical vehicle charging optimization, because most of the time people directly connect their EVs to their own plugs, right? And so they are built together, at least in the current situation. So there are lots of more applications. Konrad gave some examples about loadings and like for maintenance and etc. If you have any applications in your mind, I would be happy to hear those, because because it's basically very important in my opinion for the future of smart grids, and the possibilities are endless. So privacy. Maybe you heard that like the smart meter data are very private, but maybe you don't know why. So there is this thing called non-intrusive load monitoring, which is proposed in a very naive way. It's basically a disaggregation. So as you know, like a consumption or the energy usage is some sort of like cumulative, additive. So if you use their cooking, cookware, washing, like the TVs, lighting, they all added up in the smart meter readings, right? But for example, demand side management, if we could measure all of these separately, it would be amazing, right? So that we could say, okay, don't wash your clothes now, do it in the night because there's a peak time, but we don't know when do they use their washing machine. So it turns out these appliances follow certain patterns, and signal processing helps us to disaggregate these patterns from this aggregated consumption, which should be great, right? But this brings some privacy problems. Maybe I don't want to show you when I use my washing machine. Maybe I don't want to tell you when I wake up in the night, maybe for, I don't know, during the Ramadan times. Most of Muslim people wake up in the nights, right? So you can, the maybe the supplier or the system operator can easily deduce that you're a Muslim and you don't want to share that. Or basically, the most basic example, someone can identify when you're at home or not, and you don't even need non-intrusive load monitoring for that, right? So these kind of things make smart meter private. So yeah, I told about it, potential to reveal personal habits and routines, some unauthorized access to sensitive household information, of course. So these bring data accessibility issues. In Europe, we have GDPR, and these restrict the availability of the detailed smart meter data. And these also brings lots of challenges for system operators or utility companies, suppliers to share this data. And we need this data for future developments, not only from the company sides, but also from the institute sides, educational institutes, or like us, like the academicians and everything. We need the data for writing our papers, developing our models, right? So if we don't have the data, at least for in terms of smart meter, we cannot develop good methods. So this slows down the innovation, and we lag behind, and there's no energy transition in the same pace with, I don't know, like computer science or healthcare, etc. So it's a problem. So what can we do? There are a bunch of things, there are a bunch of propositions, which I mean, all of them have their own drawbacks. If they wouldn't have, we would be using them already. In my take, is like, if our problem is only sharing the data, I say maybe we can share we can model the smart meter data so that we only share the model or its outputs instead of the original data. So this outputs is gonna give similar patterns, but not exactly the same. They are gonna cover the same statistics, etc. You can use them in the same way, hopefully, like the original data, but it's impossible to deduce where the data comes from. Okay. Some disclaimer. Of course, there are more than one method of modeling smart meter data. I will only be referring to generative modeling of smart meter data, because there are some expert-based modelings to using these appliances, etc. But I'm gonna go only in the data-driven probabilistic way, right? So until this point, do you have any questions? Yes, Conrad. Not the expert base. Why do you use data for your cable studies, not the expert base? Yeah, exactly. Because like as human, it's limited that we can know about the complex patterns, right? I mean, I'm gonna already talk about it, but we say, okay, we have lots of data. Let's say in the case of smart meter data, there is lots of data. We don't have them, but there is. Maybe like the utility companies have those. There is lots of data, and it's really hard to understand. And every time there's a new technology pattern, for example, EVs, how can maybe 10 years ago, we could do the expert-based modeling. But with EVs, we should do them again, and again. But instead, we can just collect a bunch of data with EV houses, like houses with EV, and train a new generative model. So it's the same mentality with ChatGPT. Instead of using the expert-based bots, you just retrain, reinforcement learning, etc. So data is always more efficient, let's say, than expert-based. So generative models. So this actually image actually it was very popular, like, I don't know, 5 years ago, to open some AI-based lectures, because the natural question is, okay, how many of you think, okay, this one is a generated image or a real image? And these, and these, and this. And it turns out, okay, it's like all of them are generated. But today, of course, in the age of ChatGPT and DALL-E and etc., it comes pretty normal right now. But by that time, in 2019 or something, it was super weird, you know, like, because these are super realistic, and this person does not access. So you can go to the website, it's gonna just generate a random face for you, and it's super realistic, right? And it is a right now, very primitive model. Then the DALL-E came into place. It is also old, by the way. By this time, like, it was 3 years ago or something. This was like popular. You can right now create art. You know, you can write some prompts, and you know, like, you can generate content, let's say, which is like dreamy. It's 10 years ago, you couldn't even think about this kind of things. But there's also this thing, file transfer, which is actually similar to what we want to do. We're not using exactly this kind of methodology to these kind of things, but I think it's a good showcase of what are the possibilities, because, you know, if you're Vermeer, let's say, if you don't want to share your girl with the pearl earring, but art studies, you know, like, students in art studies need that kind of data for, I don't know, some analysis on anything. Maybe you can share these instead of these new generated images instead of the original one. They still follow similar artistic style, similar content, etc. They are similar, but different. We sort of plan or desire to use this kind of approach with smart meter data sharing too. So some introduction. First of all, why is this so impressive mathematically? So you know that, like, these data at the end of the day is, even if it's like an image, at the end of the day is like just some numbers in your RAM, in your computer. So the mesmerizing thing is they reside in a very high dimension space. For example, for a 1,000 to 1,000 image, it's like 1 million, more than 1 million dimensions. It's incomprehensible. And forget about processing these in an efficient way. Most of this space is also empty. You know, like, okay, this is a 3-dimensional space, but imagine, like, it's like 1 million dimensional space, and most of the time, the meaningful data resides in a manifold. So most of this space is basically noise. If you take a random sample from the space, it's not going to give you a Vermeer painting or, you know, like a teddy bears. It's going to probably give a noise. So it's really hard to disclose this information. For us human, it's really, I mean, nearly impossible to comprehend this mathematically or algorithmically. We just cannot do it, right? So the benefits, what can we do with this data? Okay, it's really nice that we can generate some nice images and etc. But us engineers, what can we do with this, right? So there are some, I mean, I can take your takes from this, but in my idea, here are some benefits. We can generate some novel test data. So you can say, okay, how does my system or process perform with unseen scenarios? We can generate some scenarios to test our models. We can generate large amounts of training data for other machine learning models to avoid or mitigate overfitting, like including adversarial models. But of course, there is no free lunch. We cannot generate more information out of a limited information, but still we can trick some models. So we can also embed some bias in the generated data. We can impose some physical constraints in the model training. We can also try to generate, like the extreme scenarios, like extreme weather condition scenarios that are missing in the original data a lot. So we can, we can put some bias during the data generation. Yeah, and of course there are lots of possibilities too. So what do we want from a generative model? Some soft objectives. Individually, they should be realistic, for sure. We want our samples to be plausible. They should generalize from the training data. Of course, the third is fine. Okay. The model should generalize from the training data, of course. What happened? There may be some privacy ownership concerns over individual data points. We should be considering those. And lastly, collectively, samples should look like the population, right? There are, I cannot cover all of them, but there are examples that these are not considered individually, and we have to consider all of them. So objectives are a little bit more theory right now. So we assume that every data set is a collection of samples from an unknown real-life probability distribution. So this is the key, right? So we say whatever data we get, actually, okay, there are two kinds of data, in my opinion. One is the simulated data. For example, Gabriel does that, right? So you simulate and you gather the data. There's no randomness in that because you're in the control and you try to replicate the actual simulation. But this is a different kind of data, and there's data that we collect from real life, and they are intrinsically random. Sometimes we call this randomness like noise and etc. around the function that we want, but still they are random. For me, there is no noise or anything. Every data coming from a probability distribution, but we cannot observe that. So this X means data set. In real life is like our unobserved distribution, and there were samples somehow we gathered in time, in space, or whatever, and we collect them in a data set, right? So the main motivation, if we can estimate P real life X as P theta X, which is a model, and theta is the parameters, we can sample more data from P theta X, which means synthetic data generation. We can use P theta X for lots of things, for like dimensionality reduction, for outlier detection, for lots of things, for deducing lots of things. But in my case, I'm gonna use it for sampling. The very cool thing actually, because at the end of the day, these are functions, but these are functions that you can take samples, and at the end of the day, samples are sometimes like paintings, right? This is super nice. So one question is, how are we gonna choose theta X, right? So there are infinite options. For example, okay, there's like one dimensional data, and we have 3 data points, right? X1, X2, X3. And we want to model, or we want to fit a probability distribution on that. Like, which one do you think is a better fit, right? So like this one, I don't know which kind of a distribution is that, but let's say this one, or a simple Gaussian. How can we know? Like, or which parametric family do you want to choose? Those are the questions. So we need a mathematical objective to decide this. We want to minimize the dissimilarity between P real life X and P theta X, right? This is pretty obvious, right? So in probability and statistics, there's this great metric. It's not a metric, but it's like a measure, let's say, called KL divergence or divergence metric. It compares probability distributions. It is 0 if and only if the two distributions are the same. Else, it's positive, right? If there's a discrepancy between them, it takes a positive value. So basically, we want to minimize this, right? And so that we want to find the parameters that's going to minimize this. Actually, I have a demo for that, but I don't think we have time to cover it. Yes, so like I'm going to skip it now, but you can access the slides later, of course. So KL divergence is great. We want to minimize the discrepancy between the model and the real life distribution. But you might ask, if we know the real life distribution, why do we even bother to model it? And here's the catch. Of course, we don't know the real life distribution. Instead, instead, we only know the data distribution. Actually, the data itself. I mean, but still, we can model the data as a data distribution, like empirical data distribution. So we instead minimize the KL divergence between the data distribution and our model, which makes sense, right? So only way that we access our real life distribution are these little arrows, which are Dirac delta functions, which indicates the data points, right? And if we rewrite the KL divergence, as you see, it's basically, our objective is basically maximizing the log likelihood. You might know it like cross entropy, etc. Minimizing the cross entropy is basically maximizing the log likelihood. I'm skipping the math right now. So basically, you want a probability density function that covers the data points as much as possible, right? You can see, maybe you can, little points here. They are like the corresponding likelihood values on the probability distribution. You take these values, take the logarithm of those, sum them up, and it's your objective. Great, right? But since this is a probability density function, it should be positive, and they it should, not the points, but the function itself should integrate to 1. So it's the constraint optimization problem, right? But of course, at the end of the day, we always use some known distributions or parametric families, so they always satisfy these conditions. Great. So it's great for lower dimensions. So I mean, you can basically do this with a Gaussian, and it basically gives you the mean and the standard deviation, and you're done, right? If you know that it's going to be a Gaussian. And also, if you go to higher dimensions, you can model the covariance matrices, etc., etc. But if you want to model very complex distributions, like in the case of like the paintings, etc., etc., you have to go higher dimensions. Then modeling choices becomes very infeasible. So our goal is find a parameterized probabilistic model P theta X, actually, where X is very high dimensional, right? And these X's, each axis, each feature, they are somehow correlated, dependent, or like the very related to each other, right? And we want to disclose this relation like this. We want to find a Px. This consists of like the features, the number of features, and we can describe it as a conditional chain. Okay, but the problem is finding these relations between many features is exceedingly hard, even for us. I mean, even for the current computational resources. An example: there's some math, and the chain that you need, like the k is the number of probabilities that you need per dimension, etc. And as you can see, for a 16 by 16 image, which is it doesn't mean anything for us, but it means like 256 dimensions. For black and white image, it means either 1 or 0 probability. It's 10 to 77. parameters. For grayscale images, it's 10 to 616 parameters. And for RGB images, it's like, I don't know, I mean, it's impossible, right? Like, these are like, I mean, impossible to model this kind of thing. So you can imagine for 1,000 to 1,000 image. We need something else, right? So what can we do? Yeah, as always, deep learning always helps and runs in saves the day. And to mitigate this kind of issues, instead of deciding this kind of relations, we put things into neural networks and they somehow figure out. But maybe you're all just accustomed to maybe classification model of feed for neural networks, convolutional neural networks, etc. But for probabilistic modeling, you need more. You can still use neural networks, but you have to shape the structure. You have to adjust the structure and the progression and the objective function. So we have a bunch of options for these. So we can overcome these problems with the high dimensional thing, right? Great. I'm not going to explain this in detail, but in the second part, I'm going to talk about VAEs. Let's check the time. And actually from here, okay. So until now, do you have any questions? I think might be it. I try to keep it a bit high level, but if it's okay, okay. So yeah.
So thank you for the nice presentation until here. Just I have two questions actually. So the first one, can you explain more how the data you are generating are realistic? So how you can guarantee that the data is realistic? This is the first thing. And just in the slide 24, I think. It's like just curiosity. So you said that the problem is a lot of features. So it's a hard problem. So I have the opposite problem. So I have no features in my data. So there is any method that like when you select number of features, so you can get a very good synthetic data. Yeah.
Yeah. So for the first question is an open research topic about realism of the generated samples, because I mean I'm gonna already talk about in the challenges part how to test or how to see if my generative model is doing okay or not. It's an open problem because maybe it's you sampled 10 samples, right? And if they were all realistic images, how do you know the 101st is not gonna be like a noise or something? So it's really hard to assess. But I can say if you have enough data, at some point you trust the network. And actually, in the case of like DALL-E and everything, they're pretty much okay. And I can maybe add, like what ChatGPT does may help with the reinforcement learning. If a generated image is good or not, they can be flagged and etc. And they can be retrained. That can be a solution. And for the second one, I mean, I'm gonna also talk about the smart meter data just in 1 minute. But when we talk about time series data, it's also can easily be high dimensional, right? Instead of taking like daily profiles, you can take monthly, yearly. If you take more, you can find the relations between the, let's say, days more if you take weekly instead of days. Daily. So it can easily, the high dimensionality can go higher. So, but of course, this challenge, it doesn't mean it applies to everything, but still, like I believe generative modeling, generative networks, etc. Still, even if this is not the case, they still work good in low dimensions too. It doesn't necessarily have to be a challenge if you're gonna apply the. I mean, of course, you can use some Gaussian mixture model, basic distributions to model your data, but these already have lots of benefits. So depends on the application for sure. No, there's no free lunch. Exactly. Exactly. This was actually one of my research gaps and research challenges at the beginning of my PhD, because normally you can say that, okay, the generated image looks plausible, right? You can say, okay, it's good or not. But in time series, no. I mean, even if it's like smooth or anything, how can you say, okay, like smart meter time series, not like stocks or anything? How can you say? You cannot. So it requires some sort of an expert knowledge for to assign those kind of things. Yeah, for sure. Thank you for the question. So let's move on to the smart meters part. It's basically, and by the way, I'm gonna, in this case, I'm not gonna be super technical, and actually I'm gonna do some bypass, because I'm gonna say, okay, we're gonna assume smart meter data not as a time series, but a collection of snapshots. So we're gonna do some tricks there. So since we're gonna have some snapshots, we can concatenate them in vectors, and after concatenating them in vectors, these are we call them profiles, or daily profiles, weekly profiles, whatever. These snapshots are basically some numeric points in some sort of metric space, right? So after we're getting these data points, they're basically x's. So we can apply our favorite generative model to our snapshot data sets, right? It's pretty basic, but with some challenges, of course. Nothing comes free, no free lunch, right? So we have lots of data X options, which are like generative model options, neural networks, etc. These are very powerful, versatile, and almost all the time ready to use. After some modification, you can just use any GAN, VAEs, or whatever. It's great. So what can go wrong? Here are some challenges. First challenge, too much flexibility is not good. As you might know from your regular regression and classification models, there is something called overfitting, right? And this is not the exact same case here, but similar. To understand this, here's some intuition. It said we can model the data. Actually, data itself is random, and we can model it with Dirac delta distributions, which is basically also a probability distribution. So you can think of it as these are data sets, and we take random samples from it. It's like a random process, right? Okay. So, and we also said we want to minimize the scale divergence between our model and the real life distribution. Since we don't have the real life distribution, we have to use data distribution. But maybe you thought about it or not, but is it okay to look like the data distribution? I mean, do we really want this? Because, you know, if like our objective forces this, our model to go to data distribution. So do we really want this? Because, for example, imagine your ground truth is basically a normal Gaussian, right? Like a normal distribution. So we have like a limited sample from it. And since we have like a biggest model in the world in the generative modeling, if you try to train it with these 3 data points, of course it's gonna try to replicate these data points. Do we want it to replicate these data points? No, because like I can take the data sets and put it like, okay, the best generative model Kutay 2.0, like, and put it in internet, and I can still give like random samples from this data set, and I can say, okay, it's the valid it's a valid probability distribution. It's a valid generative model. So, but we don't want this, right? We don't want to overfit to the data. It doesn't mean it. We want our model to generalize. But this is not the only problem. The objective function that we want, like log likelihood, this for sure maximizes the objective log likelihood because it's the unbounded one. It takes the objective log likelihood to infinity, but only one point converging to or copying, overfitting to only one data point is also takes the log likelihood to infinity. So your rest of the data might look okay. We don't know, but still, you can just your training, validation, anything can just crash or say very good things about your objective function just by copying data at one data point. So we don't want this. We don't want data copying. We don't want overfitting. And another thing is like these are really hard to find in the validation case because you have to check every data point. You know, you should take samples and you have to look at them because not all. Sometimes these are like a bit noisy and the log likelihoods are not super high, but still like they are basically the noise version of the inputs that you train with. So, okay, some key takeaway messages. And I'm very serious about this. Individual data points have no uncertainty. There's something called aleatoric uncertainty, and we cannot represent this aleatoric uncertainty in the models because data points intrinsically there's no uncertainty in them. So only information we have is the data set itself. It's not possible to produce more information out of a limited information. We don't know anything about the middle points of these data points. So this is the challenge to overcome for sure. Yeah, I already talked about aleatoric uncertainty. Same as that. Yeah. So uncertainty modeling is not I think it's very easier in terms of the model than the uncertainty coming from the data itself, data points itself. Yeah. So you might ask the first question. Okay, we use validation sets and yeah, holdout sets, etc. in the supervised settings. Can't we do those to see okay if we're overfitting or not? But unfortunately, it's not the case for generative models. Evaluation of these generative performance is not straightforward. We can do two things. We can check the log likelihood of the test data, held out data, etc. Or we can check the generated samples. Or we can do both. Why not, right? But there's this very great paper that actually it's like 2-3 pages or something explains why not. Why can't we do that? So imagine you get poor likelihood scores, but great samples from the test set, or like you poor likelihood from the test set and great samples from the model. It's basically the overfitting case. You just pre-sample from the data set distribution. When you put the test data, it gives terrible results, which is very expected. Yeah. But what if we have great likelihood, but poor samples? Because of the very high dimensionality, even if we could model the real life distribution, but at the same time, a noise, right? We could, because of the log likelihood and because of the dimensionality, we're gonna have great likelihood scores because they scale with the dimensions. But if we try to take samples from the model, there are always gonna be noise because it's 99% of the time, or 99% of the time, it's gonna be noise. That's 1% of the time, it's gonna be real data. So it's gonna always give bad samples. What about, you might think, what about if we have great likelihoods and great samples? but still, we can, instead of generating noise 99% of the time, we can generate the data set. We can copy the data set and give the data set again for 99% of the time. And just 1% of the time, we have the real distribution. Still, it's the same scenario. So it's not easy to validate if we're doing good or not. So some takeaway messages. Evaluation of the generative model is still an open research topic. So if you use a generative model for your own research, please don't take it for granted. The scores and everything coming from the training, etc. Yeah, again, don't trust your log likelihood values if you have any ungenerated samples. Because, by the way, these log likelihood values, not all the models give you this. GANs, the generative adversarial networks, for example, they model this implicitly. They don't give the log likelihood to you, for example. But some models give, and in our case, we consider like, okay, we have the log likelihood, sort of. Again, validation or test strategies are not sufficient for good generative performance, for sure. And also, again, the same topic. What does a good generative performance mean anyways? How can we assess the generative performance? Because I counted 4 things, right, at the beginning about what do we expect from a generative model. How can we assess if it's doing good or not? This is still an open research topic. And the last part, of course, the privacy. We didn't talk about privacy. Why? I mean, because some people, some researchers think, okay, yeah, synthetic data generation is a silver bullet for privacy issues. If it's like a synthetic, it should be private, right? But we already seen that, okay, overfitting can happen, and actually not even overfitting, data copying can happen, and your privacy is gone. But the problem is this. So we know, okay, if overfitting or data copying happens, then of violation. But other way around is not necessarily true. We don't need overfitting or data copying necessarily for privacy violation. Yeah. And while privacy, even if it does not copy any data, of course, one of the examples is it's not only testing mechanism or like the attacks that we have, but membership inference attacks. You can still deduce. I mean, this is not exactly how does it do it, because in the higher dimensions, it's super hard to do these kind of things, but it's like an intuition. If you want to talk about the membership inference attacks we can use, it uses some shadow data sets, etc., etc. And it's basically, it wants to decide a given point if it's used in the training or not, right? It's one of the many attack models for the generative models, right? And this actually, this picture gives just an intuition about, okay, even if we model the distribution, we can still deduce somehow if we slightly overfit. I mean, it's not overfitting, of course, but we can slightly understand, okay, where are the data points? It's still a guess, right? You cannot attack 100% with 100% accuracy, but there's also levels of privacy. So depending on these overfitting levels, let's say, you can still deduce, okay, this model is how privacy preserving it is or not. And some people, some researchers also try to use some Euclidean distance, or basically distances for assessing how are we similar to the original data points? Are we far from the closest neighbor? So if we are far enough, so it's not private, etc., etc. But I say it's not the case in heavily correlated data, like images, like time series. If you put lots of noise around it, which is the case with differential privacy, by the way, if you put lots of noise around it, you can still be very far in terms of Euclidean distance. Of course, you lose information, you lose But since these are heavily correlated, there are lots of mechanisms to remove this noise, right? If you put this kind of noise on top of this time series, you can still see like, okay, this is like, I know this data is basically this, right? But in terms of Euclidean distance, probably this is far than this data point, which are very similar, very different. So the idea is data, meaningful data, again, resides in a manifold. And we have to generate realistic images on that manifold. Otherwise, Euclidean distance doesn't mean Euclidean distance doesn't mean anything, and the distances should be taken on that manifold, which is not Euclidean. So it's a different kind of distance mechanism to attest privacy. And again, some takeaways. Synthetic data is not a silver bullet for privacy. Assessing privacy preservation is not straightforward for raw data, again. And there's no consensus on the mathematical definition of smart meter privacy. This is not something that I talked about, but privacy definitions are already super blurry. For tabular data, it's pretty much established, but for smart meter, we talked about non-intrusive load monitoring, but we never mentioned it again. So because GDPR is super strict about it, it doesn't matter what information it contains, smart meter data is private. So in order to mitigate it, you need to define some sort of a privacy definition. But we don't have it yet, so it's a bit of a problem. So we don't know how to test if we are preserving this privacy or not. Instead, we concentrate on the data privacy, or like the mathematical privacy definition, like the what do they contain in terms of information, etc. That's one of the problems. And we don't have, we also don't have attack models in cybersecurity. Maybe tomorrow Nicola can talk about it more. In cybersecurity, there are some very well established attack models. We experienced those, we saw the effects, etc. And we test on those kind of scenarios. I don't know, probably. And we check if we are mitigating those or not. But it's not the case in smart meter privacy because we never experienced that kind of a privacy attack. We don't know what are the consequences, what are the attack vectors, what are the parts that prone to privacy violations, etc. We don't even have a synthetic data sharing platform to see what happens or anything, right? But it's evolving right now. There are lots of nice platforms going on right now, and hopefully, I don't know. Hopefully, we're not going to have some attacks. But in terms of research, it would be nice to have some examples. Like the Ukrainian case in the cybersecurity literature. We don't have that kind of a thing in the privacy literature. And some honorable challenges. These are the last slides, I promise. Yeah. How do we include the user level statistics in the model? Because of course these are we're talking about the data sets, not individual data sets, but data sets collected from lots of customers, right? So for example, you want to aggregate them on the feeder level, and the generated data should actually add up to the original aggregated consumption level, load level, right? We have to integrate those into the model. Also, for example, if you want to work on tariff design, in time, not in space, the aggregation should be preserved, right? The total consumption should be preserved. These are not covered yet in the literature. Some spatio-temporal constraints. Actually, this is the things that I want to say at the first, but also from user level statistics, we care actually in the synthetic data sets. We don't want a user data imbalance. If we don't want lots of data representing one user and just a few data representing the other one. So we want to cover some user level statistics. And so also how do we induce the privacy? It should be privacy by design. Should we modify our generative models? considering the privacy, or should we just generate bunch of data and check which one of them are like violating the privacy or not? This is one of the other questions, but GDPR promotes privacy by design, as a side note. And I think the biggest challenge, how to convince privacy officers and lawyers, because we're not speaking the same language. I've spoken a bunch of those, not bunch of those, but like I spoken with more in the social side people from the privacy law, etc., and also like the privacy officers in DSOs. I mean, they also sort of unsure. They know what they shouldn't do, what are forbidden, but they are not totally aware why, right? If we don't know why can't we do something, it's harder to overcome that. So even if I find the best privacy preserving synthetic data generation mechanism, how am I going to convince the privacy officers and lawyers in the daily, not even in their language, in their language, in the law language, right? So it's, I think, one of the biggest challenges. That's pretty much it. So some conclusions: smart meters are crucial for modern energy systems, in my opinion. If you have any other opinion, I would like to hear, because some DSRs also like maybe prefer to, instead of using smart meters data, I just don't bother with the GDPR and just go and install more PMUs or SCADA system. I'm sorry, digital measurement devices to the substation. That might be another option, of course. But in my case, in my opinion, smart meters are super good for sustainability for future smart grids. And I say modeling smart meter data helps in generating synthetic data and enhancing grid management. Of course, I mean, not only grid management, but still. And deep generative models are great for this task, but come with challenges. And you should definitely consider all the time, not only for smart meter data generation, but for all your tasks, the challenges and the pitfalls of the deep models. That's all from me. Thank you for your attention. If you have any questions, I can take it